All right, it is 3:45. I believe it is just the three of us with MEA, is that correct?
It looks like one more person is signing on.
Excellent. Maybe if everybody could just introduce themselves briefly in the chat box so that we know who's here and what your interest is with the meeting, kind of what you teach or what your affiliation is with education. I have a little bit of an echo on my side. Am I echoing for all of you?
I don't hear it, Chris.
Okay. So each monthly PLC for this series is going to focus on specific practices that were recommended to national level and Montana through the National Research Council in 2012. And this particular month is developing and using models. And this is two excerpts from the text, K12 Science Education from the National Research Council, and their specific definitions of science and engineering with models. And so my question to the audience is, what particular verbs in the science definition do you see that you think is very important? I'll start the science portion. So when I look at the science definition from a framework for K12 Science Education, I see the word use and develop in here, which is part of the practice, developing and using models. And the purpose for developing these models is to use them as explanations. And so that particular definition in science really helps me understand what the purpose is for students developing and using models. Anybody want to take on the engineering part and see what the purpose is for using those models in engineering?
The one that jumps out at me is analyze.
And analyzing systems specifically for solutions, and so that cross-cutting concept is really in there for the whole thing for engineering, which is really powerful. This is page 50, if you were wondering where to find that in the book. We're going to look at some progressions through grade bands. Do we have our fourth person on as an introduced? I'm unable to see that.
Rachel from Butte is here with us.
Oh yeah, that's me.
Hi, Rachel. Good to hear you again.
Yeah.
So progression models are progressions through the grade bands for developing and using models. I have some very specific verbs for each grade band. So maybe what I'll do here is assign each of us a grade band to look at. If Colette, if you wouldn't mind taking grades K through 12, Rachel 9 through, or K through 2, not all of it, Colette, I apologize, just K through 2. I'll take 3 through 5. Michelle, if you do 6 through 8, and Rachel 9 through 12. And what I want to do is I want you to take about 2 minutes to look over that specific grade band and pick out verbs that you think are really important to describe how students in the grade bands are developing and using models according to NGSS's recommendation. And so I'll give 2 minutes starting now. Okay, and before we share out, something that I like to think about with this progression is that it does help us understand either where our students are coming from or where they can go. But there is a little bit of a deeper sense of this in that we're just beginning this in Montana. And so a student who's in grades 9 through 12 may have only had explored this developing and using models progression maybe at the level of 3 through 5, if it's the first year that they're getting into it or the second or third. That is also saying that this is a great way to think about differentiating and using different sorts of specialties for students with varying capacities in your grade level. So even though you might be at 3 through 5 or 6 through 8, so you might have a student who has a capacity to build and use models at grades 9 through 12, or may need to step back a little bit and do it at grades 3 through 5. And so this is a great way to look at differentiation in the classroom as well. And so K2, what verbs stuck out to you as far as the practice in the classroom and what those students are doing?
Well, the three words that stood out to me were develop, that students are actually developing models, but they're also using them and then comparing them. And I think that's really interesting to think about at that K2 level, where maybe, like from my preconception, I might not think of K2 kids developing models. And so that I thought that was really interesting and a great way to approach those kind of higher levels of thinking at that younger age.
Awesome. And I like the examples that they include at the top where it's in parentheses, where it's talking about even a dramatization or a storyboard could be utilized as a model at that grade level too. And so yeah, I think you definitely nailed those verbs down. And in grades 3 through 5, identifying the limitations is something that as a 5th grade teacher I found to be very powerful, you know, kind of that concept attainment of knowing what something is as well as knowing what something is not. Where do those models fall short? Maybe it's a redesign, or maybe it's falling short in one of the cross-cutting concepts, such as cause and effect or function or scale. And so I really like that in that grade level, specifically 3 through 5, they're starting to identify limitations. About 6 through 8.
I liked everything where you could really see, you know, because middle school is where, you know, they're going beyond concrete. Well, 5th grade, hopefully going beyond concrete thinkers, and it takes what 3 through 5 is and builds on it, where in 3 through 5 they're identifying the limitations, in 6 through 8 they're evaluating those limitations of a model. And I liked how they had, instead of just develop and use, they have develop, use, revise, and predict, which I think is through all the grades, and then to generate data from what they do.
Awesome. What about 9-12?
Yeah, I think they all are building on each other. So I also had evaluate, develop. I thought some really important ones from 9-12 were to predict the relationships between parts of systems, and then to generate data in order to predict and analyze a situation.
Awesome. And something that isn't necessarily spelled out in this progression that is in the DCIs is K through 5 is really working on a macro scale. And so thinking about just that scale, proportion, and quantity of models at those grade levels being on a macro scale, so being able to see those with the eyes, the phenomena that they're describing. And in 6-8 really focuses on a micro scale, and then in 9-12 macro and micro are studied simultaneously and compared. And so if you're thinking about that as far as developing and using models, it provides a little bit more information. My colleague Amber Lloyd used this in her classroom. This is the Upgoer 5, and it's designed to generate conversations about how in science and engineering, why is vocabulary important at the modeling level? Why is vocabulary important? And just first thoughts about what you're seeing in this image.
It's exciting because it's a rocket.
Yeah.
I love the bottom part where it says lots of fire comes out here.
And so there are a lot of adjectives used, what we would typically break down. You know, if we're talking about phenomenon in science, we break that down with Latin words and try to include a lot of information as we describe species and other phenomenon. But it goes for models as well. And so this is leading into the next slide, which is talking about in pedagogy, what are those vocabulary words that we use to describe models themselves? And so model, prototype, design, solution, product, and version. And these are things that we see in marketing or through products when we are at the stores or looking at designs for things that we might want to buy, but it's also things that we can be using in our classrooms with specific words. And so when you see these words, think about how would you level them? I mean, what would come first? What would be toward the end, where you would be at the end of a project or the end of a engineering challenge? And what are kind of those middle phases when we're looking at developing and using models.
Testing and revising?
And so when we're testing and revising, would you think that that would go into like solution or design or prototype? When we're doing that in the classroom, what words are usually attached to that?
Oh, maybe I misunderstood the question. Never mind.
No, we're onto something for sure, because when we are first creating something for either to describe a phenomenon or to design something in engineering, to design a solution, right? We end up with the solution or the product, which is the end result. And that maybe even comes in different versions, right? And so we could have version 2.0. And so the solution or the product, even though it's considered the end result at the beginning, is still revised and resold. And so when we're just beginning those models and we're testing a portion of that model in a way that is maybe cost effective, we're kind of looking at a prototype. And I think that what you were talking about as far as testing would fall into that prototype category.
Oh, okay.
So then there's a few other words that we do not see in developing and using models, and my question is, are these models? Because we have a completely separate practice for this, as recommended to us by the National Research Council, and that's using mathematics and computational thinking. And so is a graph, a simulation, a formula, or an algorithm also a model?
I think they all are.
I agree.
And maybe they're part of the data that we use as evidence as we're testing different prototypes and getting to that end product. But these are kind of the pieces of evidence, or how we look at the data that's produced when we're in that iterative process of trying something new and testing out what we want to test out.
Yeah, absolutely. And what's amazing about the practices is that they rely on each other so heavily. They depend on one another. They're interconnected in so many ways. And a lot of them, it's almost impossible to use them separately in a context in which you're solving a complex problem. And so what is powerful to me is that we really have two different practices that are talking about models. And one practice, using mathematics and computational thinking, is models in mathematical and in computers. And so really there are two modeling practices there. One is more of the traditional sense of what we think of as a model, and then the other one is in the mathematical sense. And in a PLC coming up, we will compare using mathematics and computational thinking and analyzing and interpreting data, because those are so interconnected that sometimes they are hard to separate and often are not naturally separated, but understanding the difference between the two and how they support an argument or choosing a solution is really important. But also taking that mathematical thinking and computational thinking and relating it to developing and using models, I think, is very powerful.
I think it's really important too, because in the last PLC, the common statement that was repeated was students having a hard time either moving from the model to the mathematical piece, or from the mathematical piece to the model, or actual using it in real life.
Right. Yeah, absolutely. And so when we look at this next slide, I have mental models as a strike through, because when we're looking at developing and using models, we are kind of attacking and pulling out those mental models from students that can hold some misconceptions, and we're moving them into physical, shared, and clear models, which can be an analogy or a diagram or a simulation, or also a mathematical formula. And so when we get into that mathematical formula and simulation more on the mathematical side, I think it is a lot more abstract. rather than physical. And I think that a lot of times is the block for students as they move toward that. So you're kind of assigning a quantitative quality to it. And so thinking about structural, behavioral, functional diagrams and physical models, we're really looking at a lot of the cross-cutting concepts in there as well. And so going back to the definition of modeling in science to explain a phenomenon, different models explain different parts of the phenomenon, and those questions are asked through cross-cutting concepts. So often where a model falls short in one cross-cutting concept, it is really strong in another. And so looking at these cross-cutting concepts can help us with our students focus on what is this model doing really well and where does it fall short. Does it model the structure and function really well with an analogy, but fall short in scale, proportion, and quantity, or vice versa? And just looking at it through all of the different lenses of cross-cutting concepts or focusing on a couple can be very powerful as well. And so going back into developing and using models vocabulary and thinking about those cross-cutting concepts, do you see any ties between the different phases of models and those cross-cutting concepts that just pop out to you innately or that you've done in your classroom or thought about?
One that jumps to me is the scale proportion. Well, I'm thinking scale. Because if you're modeling something, something that you might want to build to fix an environmental problem or something, you would have to make it to scale.
Yeah, absolutely. And so if we think about, that scale portion that you're talking about, Michelle, the model, we might be modeling the entire, the whole thing. We might model the whole thing, but on a smaller scale. And when we get to the prototype phase, it might be only building a part of what we're looking at, a smaller portion of it, but to the scale to see if it can survive in the environment. It's just beginning to think about those questions and how they go into the different parts of developing and using models according to cross-cutting concepts.
Mm-hmm. I really think about structure and function and patterns too as you build prototypes or build succeeding prototypes, or like you were just saying too, Chris, maybe you're only building part of or modeling part of something, that you really have to pay attention to the structure and how is it serving that function. And then also, what are those patterns as you test something? What happens, and can you discern patterns as you try something and make a new prototype or make a new design? So those can elicit some of the questions that your students might want to think about as they're collecting data and looking at where they want to go next with solving a problem.
Yeah, absolutely. And, thinking about versions and stability and change, is this product, is it stable, or has something in the environment or something in technology changed to where we need to restabilize or, create another version and redesign this?
I think with my high schoolers, we talk a lot about energy and conservation because it all comes down to the bottom line. So like, are you designing a version of a product that can actually be energy efficient, that people can afford, or that is worth making as a product because it improves our lives while being cheap enough? That could be in a lot of parts, but a lot of times you see a new version of the iPhone, we talk about that a lot, that is more energy conscious or has a better battery life.
Yeah, absolutely. That's awesome.
They're probably not that interested in hot water heaters being energy.
It's a little old school for them. They definitely like anything about their phones.
It's a good hook. And so all of our Montana science standards correlate to a portion of Next Generation Science Standards. We did adapt it for Montana to fit Montanans and and what we stand for, what we do. But if you look at the Montana Science Standard, it can connect. You can connect it to an NGSS standard. And so, can you see my mouse moving around?
I can.
Yeah. Okay. Look at this. Everything works perfect. I love this version, we'll call it. And so what I've done is I've pulled some NGSS standards that are about models. And a lot of times when we're thinking about assessment and how do we assess practices, because the framework really pushes being able to assess all three dimensions. So looking at content and practices and cross-cutting concepts. And so that's a real shift in assessment. And as far as our own learning curve as teachers and as professionals in our pedagogy, one of the most difficult things and kind of your end result is how do I assess that? That's kind of our last step. And I think that not only us in Montana, but nationally, this is starting to be looked at really closely. It's like, well, where do you start? And so when I'm looking at this for my students, and I've done one for each grade band in the progressions that we looked at those verbs, I'm looking at the standard itself, and it does suggest some cross-cutting concepts as well. But this link over here labeled evidence statement is really powerful. And what happens whenever you click on this link is that it takes you to something that looks like this. And I've just cut out kind of part of that so that you can look at it in the way of a student's performance expectation. And it will talk about specifically the components of a model. And so how do you look at that model and decide, is the student are they developing and using the model? And are they doing that in a three-dimensional way? So we'll focus, I think we'll focus today because Rachel's here for high school, we'll go into 5th grade next, and then we'll kind of focus in on the observable features at the high school level. And so this is the same thing for 5th grade. And then if you would click on the evidence statement, and if you would click on the evidence statement, it looks like this. And so I'm looking at students to develop a model that has a geosphere, hydrosphere, atmosphere, and biosphere, and talk about the interactions within that. And if you really think about what that looks like in a classroom, it can be a little overwhelming, but it can also be simple. And so I have an example of that, and then we can go back and look at the observable features for these student performances and see what you think about it. Okay, and so to give you a little bit of background information of what that was, students designed their own biosphere, and they had some constraints and parameters that were set by me. And their parameters was that they needed to have a geosphere, hydrosphere, atmosphere, and biosphere in a closed system. And so the only thing that could come into the system was energy, and everything else needed to be closed in the system. And through research and designing and kind of tweaking those models, you saw a lot of different designs, including the standard 2-liter soda bottles that were put together, and then some students took that a little bit further and took 2 of those and put those together with a tube and had kind of pond life on one side and terrestrial on the other. And you saw a few of them like in a light bulb, and there was one that was in an old fish tank. And so they used a lot of different materials, and then they were talking about some of those relationships. So as a teacher, and as you're kind of watching them and listening to what they're doing in the classroom, what are some of the words on the observable features, so on this performance expectation, that you would be looking for, and how would you look for them?
For the relationships piece, I think you want to hear the kids talking about that or journaling about that or putting in their notebooks, recognizing the relationships and the interactions between parts of the systems.
Yeah, well, and just for me, being able to observe and see, do the students have those components that, like for example, statements in the geosphere, how do they represent or show the sediments or the soil in some of those examples, the water and those sorts of things. So do you see the students representing or including those elements in the work that they're doing too?
And I'm just going to kind of step back for a couple minutes and let you guys talk about this for a second.
And I think what I saw in the video was one of the boys trying to say there was water condensing. So maybe he was saying something about the hydrosphere interacts with the biosphere because it lands on the biosphere and then is used by organisms in that sphere. So if I were doing this, I'd want to see my kids giving me specific examples of how maybe resources are shared among them, or one sphere is a resource for another.
So all 3 of you have given specific examples of what you would want to see. And how would you assess that? Are there specific words in here that could help you develop a rubric, or have a conversation with a student where you're interviewing them or ask them to diagram some of these relationships on what you would consider like a unit test, or at the end of their model to see how they understand it? What might you do for that?
Well, you could, well, each of these kind of actually sets up the rubric for you. Like the first in A, the components of the model, and you want to make sure that there's 2 features that are relevant for each one, and then for them to explain how they interact.
And so, Michelle, that's exactly where I went with this when I was looking at this. It helped me develop my rubric. And so one of the performance assessments that I asked students to do is to diagram their model of their biosphere. And so what they're doing is they write it down, and then they have to label the geosphere, hydrosphere, atmosphere, and biosphere within that, within what they have designed, and explain how it meets that criteria. And then they are drawing relationships and connections in there as well. And so I asked for those 3 specific things for them. And with some students, a lot of that ends up being oral if they are assigned to scribe, or if they have other accommodations in the classroom. But most of them are able to do that in their notebooks or have a conversation with me on the spot. And so both of that is formative and summative. Or I can do it summatively and formatively is what I'm trying to say. Any other comments about this specific, looking at the performance expectations for a rubric?
I have a question for you, Chris.
Sure.
Do you do like a traditional summative assessment at all, like on a test? Did you ask them for examples, or do you just strictly gauge their learning by their notebooks and your conversations with them?
I do both. And so their notebook is all formative assessments to me, because notebook, I don't expect it to look perfect. It should look like learning. And so I should be able to see their thinking. And a lot of their thinking isn't going to be clear at first. And so it's more about the process in the notebook. And so, and I can grab a student notebook here in a couple of minutes. I'm in my classroom as well. And then they have some sort of formal assessment at the end of the unit. And so for this particular unit, the focus is on the model. And so I do ask them to write it down. They can use some of their notes, and I'm asking them to draw, label, and explain things about their model and what they know about the interactions between those Earth systems. And they turn that into me. And so right now we're working on a species and taxonomy project where they're investigating, setting up an investigation. And so in their notebook, they have all of their notes about how they set the investigation up, what their independent variable is and their dependent variable, and what they control, the procedure, and what they did was built leak packs in the stream for macro and rubric colonization. And so I can look at their notebook and understand what they're doing and have conversations with them to help. It really helps me identify misconceptions more than anything else. And then at the end of this unit, which they're working on right now, their requirement was to do their lab report. And so they had to put all of those components of the investigation into a report with graphs that were created on Excel, and then explain, draw a conclusion from the question that was asked at the beginning. And so each unit, what I would call test or summative assessment, looks very different, but it is something formal, and it's outside of their notebook, so that their notebook is kind of their thinking place, helps me identify misconceptions, and I see what they have learned by the end of the unit as well.
Okay, thanks. That was helpful.
Yeah. All right, so middle school, as a reminder, here's the evidence statement here where you would click on. The model that I focused on for this was Earth, Sun, and Moon system. And then the observables become a lot more complex the older that you get into. We're going to keep going to high school for Rachel's benefit here. Just give everybody a minute to look over the standard. We can look at the evidence statement for this one. And this one is pretty long, and it does go past the components of the model, but for our purposes today, focusing on developing and using models, let's just look at that portion of it. And what do you think, what comes to you as far as how to assess students, what students would be able to do for this standard? Everybody would just kind of jigsaw this and pick it apart and have a conversation.
Rachel or Chris, could either of you describe to me what, like if they develop a model here that's graphical or mathematical, what it would look like?
I think if it would be mathematical, I mean, really I see a lot of connections about energy relationships, a lot about what Rachel was saying earlier. And so I think it might be, if you're looking at numbers here and you're looking at graphs, I would think that it would describe those relationships.
Yeah, I would agree with you on that.
You could definitely see the progression in the standard as well as in the progressions that we looked at earlier.
Yeah, when I look at this, I don't know, it looks a little daunting to think of even my students doing this at the high school level. And I think, like, So I'm looking at A, students develop a model, and then underneath the I through V, or 1 through 5. And I think, where do they get the data? Do I just set them loose and help them find the data themselves? Do I provide data, hardcore scientific data, for each one of those? Where are my students getting their information? What do you think, Chris?
My colleague Linda Rost does a lot of this type of teaching in her classroom. And right now she's developing one for grizzly bears. And so what she does is she does find raw data, and she uses a lot of different data sets, but she'll also, instead of providing them with the data that they need only, she provides them with more data than what they need, so that they're choosing the correct data to create. That makes sense?
Mm-hmm.
Yeah. And then as they're looking for that data and trying to answer that question, they're researching, reading, obtaining, evaluating, communicating information, and a lot of content comes out of that, as well as her more traditional lessons, and then her being able to identify misconceptions and what's happening in the classroom, and what they are doing in the classroom, their performance, is dictating that for her as well. And Linda Rost is in Baker, Montana. She's kind of in the far east of Montana.
She has a YouTube channel too, where she puts her class up there doing different things.
Awesome. I'm going to have to check that out.
Yeah, she does some amazing things. And so, you know, part of looking at this, and that it does look daunting, is remembering that we're in our own progression in Montana and in the nation right now. And so this is, if we look at the progression, that would be, you know, full implementation. The student has been in this sort of system K12. And that's not the reality right now. And so as we're learning as well, and becoming competent practices. And so we might look at this and take it to more of a 6-8 level, or take more time on just 1 or 2 or 3 of these, whatever that looks like in your classroom, to help stair-step them up to the end result, knowing that longer students are in a system with Montana Science Standards that have practices and cross-cutting concepts, the more further along they'll be. And so I think the 9-12 grade band is really in a unique position, because their students are expected to have the most output, and they've had the least amount of input, you know, in proportion to how long they've been in school. And so there's a learning curve for both, and it's just about getting students to whatever level they can get to on the components of the model. We have 2 OPI people here too today, so what do you two think about that, as far as this being daunting for students who have not had a lot of experience yet?
Oh, I would totally agree. Absolutely, it is. But if you did, like you had said, if number one, since we actually are going to teach science in kindergarten, 1st, 2nd, 3rd, 4th, 5th, where that hasn't necessarily been the pattern in a lot of areas. So if you think down the road, a minimum of 14 years, it would start to look not so daunting, I'm thinking. Well, I would absolutely hope that anyway.
And I think that's really true. That's always our hope, and that's the way that, whether we're looking at the Montana Science Standards or the Next Generation Science Standards, is that we have that progression of learning that isn't just about, you know, discrete pieces of content or facts and some of the vocabulary in that, but we're actually experiencing science. Students are building that competency because teachers are creating those experiences for them K through 12. And I think that's a like I say, one of our real hopes and desires is that we see this, the opportunities for kids to learn and be scientists throughout the grade levels. That's really our hope with these standards as well. And it is challenging. That's, it's challenging for students and it's challenging for teachers. And so we're really focused on providing resources and some guidance and doing things like this PLC every month so we can have the conversations that teachers need to have in order to create that experience for students.
Does that put your heart and mind a little bit at ease, Rachel?
Or did we make her pass out and fall down in a faint?
Yeah. Well, it is daunting. I mean, I have a hard time with it. I mean, I'm K8 certified, and my question too would be, where would you get those resources? And then I think like a middle schooler, because that's where I spent most of my time teaching, and I think that if I told them to go research this on their own, find this information, then I wouldn't want them copying a model that they found. Does that make sense? Is that old school thinking? Those would be my concerns if this was put in front of me and kids were.
No, I think that makes
the work
sense.
of the teacher is to put the resources and the opportunities in place, and we really want to see an emphasis on students doing the work of science, to be scientists and have those experiences.
And Michelle, maybe those models that are out there could be used in the sense of, can they identify and critique the models that are already there, and do they have an idea of how to improve it or revise it? And that could be a really good starting point for both classroom teachers and students who don't have a lot of experience developing and using models themselves. Well, it's like, let's look and see what's been done and what I think about that, and start to think about that in a meaningful way. And we'll sharpen our skills. We'll hone our skills on that too. And so speaking of resources, this website, NASA, should be opening up. And are all of you seeing that?
I can see it.
Okay. And so NASA has a site for a landing page for every practice. And so, and those practices are throughout the grade band, so throughout the progression. And so if I go to the top, it'll give me examples of what standards this ties to. And then I can look at some of these data lesson plans. And so climagraphs, and here's some solar cell energy availability around the country. And so there are resources out there, and I think the further we go along in the nation and in the state of how are we going to assess this, we really start thinking about, well, what are students doing? We start looking at those performance expectations, and I think that's where the shift is coming in resources. Whereas when the framework first came out in 2012, and for subsequent years after that, resources were really hard to find that were outside of a lesson plan. And so this does say lesson plan, but there, we have some data sets too that we can access. And so for any practice or content that you're looking at, this is one resource. And in addition to that, and I don't, if Rachel is still here, I'm not sure if she's still here or not, but please email me if you're looking for things, and we can kind of network around the state, because there are some some teachers who are doing excellent work and have kind of dove into this and are honing their skills and sharpening as well. And so I think that collaboration is paramount. You guys see me again?
Yes.
Look at that. That's just perfect. I have a project from last year that's still alive and going. A lot of the larger ones were taken home, but this one has been sealed and going since April of last year. See, they have kind of a aquifer below, and it's not sealed perfectly because they're definitely losing moisture, but it's still functioning really well. So I have that in the classroom right now. So we have approximately 5 minutes. Are there any other particular questions, comments?
I think this has been really helpful. I did not know about the NASA site, so that's just wonderful to see that that's there. I love still learning every day.
Same. No, I think if there aren't any comments or questions, then that's my input. That's about all I have for this, and so I hope it was helpful, and I hope to see you next time. And if you're watching, please join us live so that we can have you in the conversation, because the more people we have talking and collaborating and networking, the stronger we'll be.
Thank you, Chris. I do think it was very beneficial.
Thank you very much. Thank you.
Okay, well, I will see you next month.
See you later.
Okay.
Bye.